Hello to everyone, I'm Paulo Sorricchio, master student at DigiPen Institute of Technology, and with this video I'm going to show you a project for the CS541 course, Advanced Graphics. In this project we basically implemented ray casting. It's ray casting, not ray tracing, because basically in this scene for each pixel we cast a ray in workspace and see which object it intersects and decide the color of the pixel. It's not ray tracing because we're not doing any multiple bounces and we're not doing any fancy ray tracing feature. So this is basically, as I said, the project is ray casting, and we have a scene with simple cubes, as you can see here, with different colors, and this is now rendered by OpenGL engine. And basically the problem with ray casting is that it can be slow, because for each how ray casting works is that for each pixel I cast a ray in workspace and I have to see which object of these it's intersecting, and then decide the color of the pixel. Of course, the first two enhancements that can be done for make this process faster are bounding volume. So I see if this ray, for example, this white pixel here, if this ray doesn't intersect with any of the bounding volumes, it doesn't make any sense trying to intersect with the triangles, because basically it means that I'm not intersecting with the bounding volumes that might be, for example, cubes or spheres around these polygons. And another enhancement that can be done is spatial decomposition. That means if I'm really in few words, if I'm in this, for example, in the bottom left corner, it doesn't really make any sense in trying to intersect even with the bounding box, bounding sphere of this polygon here, of this model here. And that's what spatial decomposition is. I try to intersect with as few objects as possible. Basically in this project we implemented ray casting in following the paper on building fast KD trees for ray tracing, and on doing that in O and Logan. Is from Wald and Havran 2006. Basically we use the KD tree, that is a data structure to allow, in this case for example, to divide the scene in different pieces and try to intersect the ray with as few bounding volumes as possible. And basically the algorithm was using surface area heuristics to divide the boxes as in the most optimized way as possible. And as we can see here, this is rendered by OpenGL, so it's pretty fast. We can toggle with the key G, and that might take a few seconds because obviously raycasting is still slow. But now I press G, and there we go. As we can see, we have all sorts of data here. To make this process faster, of course, the smaller the window, the faster the process is, because basically the smaller the window, the few pixels I have to intersect, even if the window is really wide, but the amount of but the area where I'm actually going to intersect is only this center area here. This pixel will obviously all be discarded immediately, because with the fast ray tracing I'm going to say, okay, this is not, there's no bounding volume here. Discard pixel. Don't even try to intersect with the boxes. So right here we can see that our main scene is pretty small, and obviously the performances are better, because as I said, the smaller the area that has to be ray traced, the faster the execution. As you say, yeah, it's almost in real time. As you can see, I can move the cubes without any problem. I put a sound every time it's finishing the ray tracing, so as I said here, it's almost real time. It's really smooth. Of course, as I said, it's small. The bigger the picture, of course, this is gonna take a few seconds. Press G, and here we go. This is I have to say, this is completely CPU bound, because basically I'm doing this computation on the CPU. That's really important. And so this is not doing any calculation on the GPU. People are coming up with algorithms and way to bring this code with these implementations on the GPU, and that would be a definitely gain, because basically the GPU are can parallelize code really well. That's what what GPUs do. They basically do little operations, but they can do those in parallel. So if you think about this situation, when I'm intersecting for each pixel, I don't really have to wait for the other pixel. I don't really care. So doing this on the GPU would be a real gain. The problem is that GPUs are not as versatile as CPUs. So on the GPUs, for example, you cannot recurse. You cannot do recursions. So that, for example, might be a problem in implementing certain kind of algorithms. And at the same point, using certain data structures on the GPU might be difficult. That's not a problem. But people are coming up with the ways, and ray tracing, it might be. People are coming up with ways to do that in real time, and I saw, you guys can see some OpenCL or CUDA examples, and those examples try to do ray tracing in real time, and they're almost there. Of course, it always depends on the complexity on the scene of the quality of the image you want, because obviously, as I said, ray casting and ray tracing are different. Ray tracing is far more difficult, because basically you have to jump the ray you're casting multiple times, see where it bounces. Different surfaces can bounce the ray in different ways, so that's not as easy as ray casting. But yep, this is project number 4. I hope you enjoyed. As usual, you can try this on your computer. Just go and download it from www.palosricchio.com, and well, hope you guys enjoyed this video.